Hey guys, this is Arsh from Don't Blink, and today we wanted to do a breakdown of our ultimate goal robot. So we learned a lot this season, especially since we migrated to using custom parts, more 3D printed parts, and generally we tried to design a cool and unique robot for the season. And we wanted to share some of our experiences with the rest of the community, hoping that it would be able to help people in the future or for Fright Frenzy even. So this was our ultimate goal robot for this season. And this was our third iteration robot. We had 3 robots throughout the season, like 3 full robots. And this was the final iteration of our design. And we kind of want to go through our timeline for the season, some of our thoughts behind some of the mechanisms that we make, and generally how we think about making these mechanisms and what goes into that process itself. So I guess starting out, we want to give a bit of context for our team. So at the start of the season, our timeline was very limited by the COVID pandemic, in the sense that we couldn't really meet in person as much as we wanted to, and we couldn't prototype as well as we could in other seasons. And while this hindered us in some areas, this also allowed us to focus a lot on CAD, which I would say was the main thing that helped us throughout the season. So as a team, we use Onshape, which is a collaborative platform for CAD, and that really helped us design a lot of the custom parts you see on our robot today. So that being said, our timeline was mainly focused on CADing a lot and then actually building. And for building, we tried to have our parts custom made so that there were lesser things to actually build. Because one thing we noticed was with our first robot, which was completely out of Go Build a COTS parts, there was a lot to assemble because of the sheer number of parts there were. But with something like this, when it's custom, so this was our main superstructure for the season. Everything can mount to this drive plane. It was much easier for us to build because there were a limited number of parts. It was like a big Lego set for us. Anyway, so talking a bit more about the robot, we can start with the Wobble goal mechanism that's just completely detached here. So this Wobble goal mechanism was used for obviously this game this year, and the main considerations with this was we wanted to not use a motor for the Wobble goal. So a lot of, like early season, a lot of teams wanted to use a motor, and we were thinking about it, but we realized it would be better used in other places. So for this reason, we have a servo gearbox over here that's just completely broken apart, but you guys can kind of see how this works. And something that I just want to point out with this Wobble goal, it's something that we didn't really give too much thought about in CAD, which might have slowed us down a little bit, but it's just something that you guys can probably take away, that it's really good to CAD everything, but sometimes in the worst cases, if you have to like pre-build a part or do some machine work in shops or use some of the tools instead of like having completely custom, it's not that big a deal. So the Wobble goal itself took like a day to build like everything here. So in that sense, it was really fine. There wasn't much work to it. It's just having a good concrete idea and design and going from there. You can see for a lot of our parts we use polycarbonate, so it's an impact resistant material and really helps with taking impacts, because this arm stuck out over here. So at competitions like MTI that were in person, really needed to take the shock. And you can see when you don't have enough support for polycarbonate flexes a lot. So down here, we had a bit of support, but it was enough that it gave us some flexibility this way. And the servo gearbox here helps give enough torque to lift this arm up and down. So the arm's kind of heavy, but since we have the gearbox, it compensates for that. The other thing is always outlining the goals for a particular mechanism. So for us, we wanted a large range for our Wobble goal. And while this might sound like a really simple goal, when you don't outline everything, sometimes it gets overlooked. It's like with our claw over here, we have a lot of range from these 2 servos. And another consideration we made is to eliminate any dead zones. So a lot of the issues in a lot of the seasons is just having dead zones in random places. So for example, with an intake, it can be where 2 rollers don't catch the ring and the ring is just stuck in place. In Skystone, it would have been somewhere like a stone gets stuck somewhere and it's just sitting on the ramp with nothing powering it inside. That was one of the problems that we had. So a lot of the things comes down to eliminating places where there could be failure, and for example with dead zones. So you can see here with our 3D printed parts, we have these 2, I guess, arms coming out. So even if the Wobble goal catches somewhere in this corner, it's not going to close on itself. It's just going to slide on this arm into the main crevice here. And that's just some of the thought that goes through the designs. Obviously, a lot of this comes with actual iterations of the parts, but I think at least for us, next season, we're going to keep this in mind going forward so we don't waste time on not having these problems solved beforehand. Another thing, so moving on from the wobble, another thing that we tried to focus on this year was being a bit more unique on our takes. So while that's something I wouldn't recommend, because to be a competitive team, generally going with the meta is always going to be a safe bet and probably going to be the winning types of robots. But a lot of times having a unique mechanism that could be more beneficial, even though it's a little more complex or could lead to some more catastrophes. Foreshadowing, but some things like that. It's fine to have that at times. If you want to have fun with FTC, which is what we wanted to do this season for a lot of our things. So you can see that's why we have something like a turret over here. Obviously, a regular shooter that didn't pivot around would be fine. You can just turn the robot, but having the turret made us have a little bit more flexibility, even if it didn't work as well as we wanted it to. So you can see here that it can rotate regardless of the robot's orientation. And this transitions to another thing in the First Tech Challenge community, which is learning from other teams. We're really thankful to teams like Primitive Data that helped us a lot with the turret, because they taught us about how the turret's held together with these bearing sacks over here. And that's something we wouldn't have known without talking to other teams, in this community, on this platform. And even things like surgical tubing is something we learned from team, Beachbots, Black Forest Robotics. And just a lot of things on here is with the help of other people, which is something I think is really important and overlooked. A lot of teams coming into this challenge think that you have to be really secretive about what you're doing, in the sense that you're not sharing designs, but in the sense that you're just not talking to teams. So if you're doing that, if you're not reaching out to actual teams, learning from them, learning how they're doing things, it's not really the best way to go about the challenge, in my opinion, because it really limits your understanding on a lot of mechanisms that you might not have experienced with before. Anyway, moving on from there, our shooter is just a one motor flywheel over here. And we hand cut our inertia wheel because we forgot to order this from Sankatsen. Again, some freehand work. And another thing is this flap. So a lot of times in CAD, especially if you're not the most experienced team, what's going to happen is you tend to forget some things, or you tend to overlook some things. So one of the things we overlooked was our shooter's angle. And so our shooter's angle is 22.5 degrees, which it's okay, but the issue is we need to shoot really fast to make the high goal, and somewhere we're right in front of the shooting line. We have to shoot really, really, really fast for it to be able to make the high goal before it hits the mid goal, or the thing that divides both the goals together. So for that sense, we overlooked the angle or angle adjustments that we might need. So we drilled holes into our thing over here. So there are two holes, one here and one here, and this allowed us to mount a hinge on here and make our flap. You can see some of the other holes were some funny mistakes, but generally we drilled these two holes, and this allowed us to mount our flap here. The flap is 3D printed because it was very, very last minute. Generally, I would recommend wherever things have a lot of contact or takes a lot of shock impact, you use polycarbonate, and for things that need a lot of structure, you would use aluminum. But for this, we used 3D printed material because it was fast, and this is really easy to prototype with, because especially if you have 3D printers at home, you can just knock out designs really, really fast. For our intake, one of our biggest learnings this year was, having less shafts is better. This is something we experienced firsthand, because our intake right now has a lot of shafts, and it takes a lot of torque from your motors. So you can see we have this one main shaft here for our front intake, but we also have 4 additional shafts for our active vectors that push the rings in. Then we also have a lot of shafts powering the active vectors, our whole transfer, and then our whole back intake, and then this top transfer over here. It's all powered by 2 motors. And while that might seem sufficient, sometimes it really hindered our torque. Funny story about this, the reason this is bent is because the elevator at MTI closed on this, but this was essentially used to knock every ring above the first one over. So that way, for something like the 4-stack and autonomous, we could just back up and only one ring goes in at a time. Another consideration we made for our intake was thinking about surface area versus actual grip and pulling in the rings. So a lot of times people are just like, oh, use rollers, oh, use tubing. what we found is that there are different situations where they work better and worse. For something where you need a lot of surface area, you generally want to use rollers because they have something that's very consistent. There are no dead zones again. So one of the things we found when testing was, you see these geckos over here. These are just cut geckos. When we had tubing on here first, the rings would actually fly out the front ramp over here. So you can see the front ramp and the back ramp here, they both meet at a junction. What happened at times was that because there was tubing over here, so if I just turn the intake really quick, so sometimes the tubing can end up sideways like this. So the ring from when we had, if you imagine tubing up here, the ring sometimes just flew out the back. So that's where we realized we need something that has a consistent surface area, but that didn't really compress the rings as much, which is where we thought of this paddle idea for the cut geckos. Again, something we learned from teams in North Carolina, like Aperture Science and Turtles. Yeah. So after that, we also manufactured this custom hood ourselves. So we have, don't worry about that. We have a custom, we have a slip roll machine in our shop, which is what we use to make this curve. You can also 3D print it. What we realized is having a thin material made it so that the rings didn't really have to go up a big bump, versus using something like 3D printed material. The actual material itself can be really thick at times. So if it's not well supported or if it's not as thick, it's gonna break. There's a storm outside. Anyway, so finally we have our last stage of tubing that just pushes the rings inside. Surprisingly, this whole system that you see here didn't work at all when as to what it was in CAD. So we had to completely redesign this, and really it was a bit of a pain, but we got it working at the end. So there are a lot of things that don't necessarily work out with your design, which is something that you should keep in mind, that if you put in things for adjustability, it's really easy to swap out things. So we learned this from teams like Brainstormers and Brainstem, since their actual structure is like very versatile in the sense they can mount different things on it without needing to take apart the whole robot. For them, it makes it really easy if they have to make adjustments, which is something we're going to keep in mind for next season. But we tried having some adjustability with things. So for example, with this shaft over here, you can move up and down because of the slots that we have. And then we just have bearing holders over here so that we don't slot the bearings, we slot the bearing holder, which is how it works. And we have slots for things like our tension over here, so our drivetrain tensioning. So we got the wrong belts, but having this in mind really saved a lot of time. And we also have slots for things like our compression for the shooter. The gecko wheel over here can move in and out. This really, really helped because we didn't know what compression we needed since we were trying out a new style of shooting, or a new shooter style. So with that, having that adjustability really helped. I would say other things that are pretty notable is we try to have motors pretty low to the ground, and like as much as possible. So for something like a turret motor, we didn't have it mounted like we didn't have it mounted horizontally on this. So if you come here on like this platform over here, we tried to make it as low to the ground as possible, which is why it's mounted right here. Same thing with things with our intake motors. Instead of mounting it directly to the intake itself, they're mounted way inside the ramp. So if you get a top view of the ramp here, the intake motors are here and one on the other side symmetrical to that. So that's just some things we kept in mind. Next season, if we can fit all 8 motors in our drivetrain, that'll be pretty fun. But you have to evaluate the pros and cons, which is another really important thing. Is it really, really beneficial for me to have all 8 motors in our drivetrain and lose on like things like complexity, or having it extremely complex, or having a lot of power transmission to get it where I want it? No, sometimes it's probably worth having motors up here. So like for a shooter, for example, we couldn't really put this motor anywhere near the bottom because this whole thing rotates, and also it really decreases the efficiency with the amount of things you're translating to, and it just makes it really complex and hard, which is something people should avoid. Apart from that, we also have some modularity. So modularity in our sense is, or there are 2 things. So we have modularity and ease of access. So for example, with our hubs, since this is polycarb over here and this flexes a lot, which is good for like impact and stuff, we can actually take these 2 screws off, and this whole hub is on a hinge, and we can just pull this out here, without taking apart the hub or doing anything weird to the wires, and we have enough slack that we can access all the wires. And this is for both hubs on either side. We also have adjustability, ease of access in the sense that all of our power transmissions on the outside. So this might sound like a bad thing to teams. They're like, oh, other robots can catch on it. We have the really important parts covered, and things that are up here still on the inside of a robot, like on the vertical plane, and they're also covered. So this really makes it easy for us to pop this off and switch out the gear ratios. And since we have things that are belted, we can change the pulley diameter size, or in some dire situations we can also use plastic chain, as you can see here. So this is completely untensioned. I think it's one extra link over here, but one extra link made it kind of tight, so we just left it a bit loose. And then lastly, we have a bit more modularity with things like spacing out with things like spacing it out, or with our 3D printed parts. So since we have a lot of access to a lot of 3D printers, we can just make a new part as fast as possible for things that need that adjustment. So for example, our main spin decks are in here that brings the rings up around this hood. We printed out like 2 or 3 sizes to test to see what worked best, and we picked the right size, and we didn't have problems from there after that. Another thing we want to talk about is something like power transmission. So a lot of teams with servos tend to direct drive things. What we found is using linkages also really helps. So on our first robot, we used a linkage for our hopper system, and then over here we use linkages for our flap and everything up and down the intake. So linkages, if you design them well geometrically, you can basically make linkages that don't backdrive. We didn't really have enough time to experiment with that and get that working for us, but what my suggestion would be is to use linkages that do that. And generally just thinking about why we chose some of these mechanisms. So for our dual intake, we thought at the start of the season, we weren't really thinking about the vertical intake meta. We were more thinking that after some early tests with the return rack, the rings went everywhere. So at least for us in a remote setting, the dual intake would have helped, because we really cannot control where the rings go. Like our return rack went everywhere. The rings from our return rack went everywhere. And then also we thought the dual intake would be beneficial for in-person competitions, especially if it wasn't something that was ridiculous, had like 2 separate paths, or made it unnecessarily complicated. So for us, we just merge the 2 paths together and bring them up one way. And since we use tubing, it's really forgiving. We can actually bring up 2 rings at once on full battery, because it has enough torque to do that. So like literally 2 rings come together as like a bundle and go into our intake and get sorted over here. My recommendation is just to think about flexibility with how you handle game elements, not making so you only handle it in one way. So like our front tubing can handle vertical rings, flat rings, stacks of rings. It can raise up for vertical rings, and then we just like raise it back down. And then for stacks, we just like press a button and it just drops onto the stacks. And it can intake all 3 and put them up when it works. And then that's generally it. So last thing I want to talk about is the custom structure. So we got a lot of our parts from Sen, and this was really helpful for us, because we were able to use a lot of aluminum where we needed for structure. So like everything here is all the silver things over here is aluminum. So it's a pretty strong material. We use 6061 aluminum for everything except maybe 1 or 2 parts that we didn't need it for. And what we did is we pocketed a lot of the aluminum. So pocketing helps with weight savings, but I'm gonna say the main reason people pocket in FTC is also for looks. It just looks pretty cool. So we pocketed a lot of things. One thing that we learned this season is that aluminum is way stronger than we think it is. So for something like pocketing up this whole big inner plate, we didn't pocket it as heavily as we should have. We could have saved a lot more weight by pocketing it a bit heavier. So for example, if you see something like Beachbot's 18253 with the Winning Alliance captain at MTI, their pocketing was really heavy on their inner plates, but since they had enough structure on it and didn't pocket where you needed a lot more stability, it worked pretty well for them, like their plates. And it didn't really, like their robot wasn't damaged once. I think it was just maybe their tubing mounts that were 3D printed, which again, where you can avoid 3D printing parts for things that take a lot of shock load, you probably should. So something like Brainstormers, they had their tubing mounted on polycarb tube, and same thing with team 5890 eliminators. They had the same thing. So in that sense, it was nice. I would say the biggest takeaway in the season is for us is, you know, we try to have some fun, but we learned that simple is generally better, and that having a really thought through process for how we want to put it together and having a design, not necessarily just CAD, but justifying why we need certain things over others was important. And I would say from that, for next season, using all this together will help our team be a bit more successful, than so that we can hope to achieve the goals that we want. That's pretty much it for this video. Hopefully it helps some of you, but our team will see you at Frag Frenzy.